Hello everybody, this is my part 3 of my lecture 3 on index properties and soil classification on the course Soil Mechanics. In the previous lecture, we have learned that an immediate understanding of the general soil behavior is possible from the knowledge of the index properties. Index properties help in proper identification and classification of different kinds of soils. We have also learnt about an important index property, the grain size distribution. Can be possible by undergoing sieve analysis or sedimentation tests, right? Sieve analysis we have seen are useful for coarse grain soils, whereas for fine grain soils that pass the 75 micron sieves like silts and clay particles, they are mostly undergone particle size analysis by using hydrometer or pipette for what we call as the sedimentation tests. We see how the results of the grain size analysis are also plotted in grain size distribution curve, which help us in determine the gradation characteristics of soil. We have also defined coefficients like Cu and Cc, which are the coefficient of uniformity or coefficient of curvature respectively, which help in defining the gradation characteristics, right? But these grain size distribution curves or the Cu and are, however, most or more suitable for identification for coarse grain soils than for fine grain soils. So in this lecture, we will see that for fine grain soil, there is another useful index property which as the Atterberg limits that help us in identifying or classifying fine grain soils, mostly clays and silts. So let's go through this. The physical properties of fine grained soils, especially clays, are considerably influenced by the amount of water present in them. Depending upon the water content of the fine grained soil or clays, 4 boundary water contents are recognized or described. At these water contents, the soil undergoes a change from one state to another. These boundary water contents are called as the Atterberg limits, or what we also say as the consistency limits. These 4 stages of boundary water contents are the liquid state, the plastic state, the semi-solid and the solid state. These Atterberg limits defines these 4 states of soil, or in other words, it tells us about the consistency of the soil. So what is consistent? Basically, it's a term which is used to describe the degree of firmness of a soil, or it tells us about the relative ease with which a soil can be deformed. So qualitatively, we can give descriptions related to consistency, like if the soil is hard, or it's firm, or it's soft, or it's medium soft, right? So we will talk about it in details, about the various defining water contents in the next slide. So before we go into details, let us draw a graph. Okay, so this is a very approximate one without any kind of scale. In the x-axis we find it the water content, and in the y-axis we express the volume of the soil, and we draw a curve like this, and we define 4 boundaries or stages as we have talked about in the previous slide. So suppose this is my liquid state, this is my plastic state, this is my semi-solid state, this is my solid state. So suppose when a fine grained soil is mixed with a large quantity of water, the resulting soil suspension is in a liquid state. That is, soil flow like a liquid and offers no resistance to flow, or we can say the soil has no shear strength. So we see the soil is in the liquid state, right, where the volume of the soil is practically very high, right? Now, when the water content of this suspension is kept on reducing, a stage will come when the soil can be remolded by hand. That means this is a stage when the sample changes from possessing no shear strength at all to having very small shear strength, and that's when we say the soil have reached a stage from a stage of liquid state to plastic state. And the defining or the boundary water content between this liquid state and the plastic state, we define it by WL, or what we say WL called as the liquid limit. Right? Now, if the water content is further reduced, the soil sample changes from a plastic to a semi-solid, and this boundary water content is referred to as WP, or what we say as the plastic limit. Okay, so in the semi-solid state, what happens? The soil has no plasticity, or we can say that at this stage the soil becomes so dry that it cannot be molded or remolded by hand as what we could have done in the plastic state. So at this state, if a simple low pressure is applied, the soil simply crumbles, or we can say the soil has turned brittle. Now, up to this semi-solid state, we see that from the liquid to the plastic to the semi-solid, the volume has decreased. The volume of the total soil has decreased. But however, up to this semi-solid state, the soil still remains fully saturated, and any reduction in the volume of water will result in the equal reduction in the volume of the soil mass. But once there exists a boundary water content, which we call it as WS, or what we say as the shrinkage limit. So reducing the water content below this brings about a state in soil when the volume of the soil mass does not decrease any further. That is, the sample now changes from a semi-solid state to a solid state, right? And further drying produces no change in the total volume of the soil, and thus we can say that the soil is no longer fully saturated, right? So these arbitrary limits, or what we wanted to say or wanted to define, the consistency limits or the Atterberg limits, right? Thus, the consistency limits are basically the water contents at which the soil mass passes from one state to another. These limits are usually expressed as percentage of water content of the soil. Right? So now a detailed definition will also be provided for these limits, and we will talk about it in the next slide. So what is our liquid limit? In short, it's the water content corresponding to the arbitrary limit between the liquid state and the plastic state of soil. At this state, we say the soil has negligible shear strength. In the laboratory, we determine our liquid limit using a standard liquid limit apparatus, which we also called as the Casagrande apparatus. We will talk about these laboratory tests in later lectures. With reference to the limit apparatus, we usually make a standard groove on a soil paste placed over this Casagrande cup, as we say, and we give blows to the Casagrande cup, and a standard groove made in the soil closes over a length of 12 meter for 25 blows. This will be more clear as we talk about the liquid limit test later. Now, what is our plastic limit? It's the water content at which the consistency of the soil reaches the boundary in the plastic state and the semi-solid state. If we take a soil and roll it into a thread of diameter 3 millimeter, plastic limit is that at that water content, soil thread will crumble down. So again, we will talk about this plastic limit test later, and things will be more clearer then. What is our shrinkage limit then? Shrinkage limit is the maximum content at which reduction in water content will not cause any further decrease in the volume of the soil mass. It is also defined as the minimum water content corresponding to which the soil will still remain completely set. Right? So these are our definitions of the liquid limits or the Atterberg limits that we have talked about so far. Now, with reference to the different limits that we talked about, now let us define some soil indices with the Atterberg limit. So as we can see, the very first indices is the plasticity index. So you must be wondering what are these indices, right? So the significance of these indices we will learn in the subsequent lecture. For now, let us first define these indices. Okay. So what is my plasticity index? So the plasticity index is basically symbolized by IP and it's equal to the difference between the liquid limit of the soil and the plastic limit of the soil. So the liquid limit we have seen defined by WL and the plastic limit is WP. Thus, plasticity index indicates the magnitude of moisture content or the water content over which the soil will remain in the plastic state. Right? So basically, plasticity is that property of the soil. We see that it allows it to be deformed without any kind of rupture. So we will learn about how we determine this plastic limit and liquid limit later in the laboratory later in this series of lecture. Now, what is my consistency index? So consistency index is linked by IC or symbolized by IC. This is also called as the relative consistency of the soil, and it's defined as the ratio of the liquid limit minus the natural water content soil to that of the plasticity index of the soil. So it's basically a ratio, right? So this consistency index is useful in the study of the field behavior of saturated fine grained soils like clay. So we will see how this index is useful and helps in classifying soils, and we will see later. Next comes the liquidity index, which we define as IL, and it's defined as the ratio of the natural content of the soil minus the plastic limit of the soil divided by IP. This liquidity index is also called as the water plasticity ratio and is usually expressed in percentage. We'll see how this liquidity index is useful in the subsequent slides. Now, talking about flow index and toughness index, for now we can just skip these two indices, and because things would be more clearer when I talk about the index and toughness index, when we will discuss how we determine this liquid limit or plastic limit in the laboratory through the standard tests. Okay, so while describing the tests, we will learn about this term flow index and toughness index. So for now, let's just skip it. Now, what is my activity number? Okay, so usually the plasticity index of the soil, that is the IP, it's dependent on two things. One is the type of clay mineral present, and another is the amount of clay mineral present. Right? So usually it's Kempton who was first researcher who came out this concept of activity number. He in 1953 observed that this plasticity index is directly proportional to the percentage of clay size particles by weight. That is, we talked about our grain size distribution in a soil sample, right? So we determine the percentage of weight of particles which are less than 0.02 millimeter or 2 micron. So these particles finer than this size represents my clay fraction, right, in a soil sample. So on basis of this behavior, that IP is proportional to the percent of clay size particles by, an index property was defined, and that property is called as the activity number. This activity number is usually represented by A, and it's given by the ratio of the plasticity index to the percent of clay size particles by weight. Therefore, here C represents of percent of clay size particles, that is less than 0.002 millimeter by weight, right? So these are my different indices that we have talked about so far, and now we will see how this are helpful in classifying different soils. Okay, so there are different guidelines are given based on this IL or IC or IP or this activity number for defining the consistency of fine grained soils. The consistency of cohesive soils, mainly clay or sometimes silt. Okay, so let's go ahead. So we'll now have already talked about the different indices, and we will see that how these indices help us to classify our soils. So based on the plasticity index, the soils are classified as given in the following table. We can see the plasticity index and the degree of plasticity on the left hand right hand column. So we see if the plasticity index is 0, we call it as a non-plastic soil, right? So basically plasticity index is the difference between the liquid limit and the plastic limit, right? So both the liquid limit and the plastic limit we can determine in the laboratory, which we will talk about later in the subsequent lectures. So from we can calculate what is our plasticity index. Usually when the plasticity index is 0, that is my liquid limit and the plastic limit is equal, right? Or we say that they coincide, right? So usually coarse grained soil are those which cannot achieve the plastic state of consistency, and we say that the plasticity index or IP is equal to 0. Also, for those soils which the liquid limit and the plastic limit cannot be determined, in case also we say that the soil is non-plastic, or we can say the IP is 0. For plasticity index value less than 7, we call it as a low plastic soil. Plasticity index between 7 to 17, we call it medium plastic, and greater than 17 we call highly plastic soil. Now based on the liquidity index and the consistency index, we also can classify the soil. Using this consistency index as well as liquidity index, we can easily study the in situ behavior of saturated fine grained soil at its natural water content. Okay, so we see in the table that from the table that suppose my liquid, so for that let me remind first of all what is my liquidity index and what is my consistency index. So consistency index is equal to WL minus W divided by IP. WL is my liquid limit, W is the natural water content of the soil, and IP is the plasticity index. And what is my liquid limit? My liquid limit equal to W minus WP by IP. W is the water content of the soil, WP is the plastic limit, and IP is the plasticity index. Now, when we say that my IC is negative, right? So we see from the very first row that my IC value is less than 0. That is, my IC is negative. This implies my natural water content of the soil is greater than that of liquid limit. That is, the soil mass will behave like a liquid. That is, it has no shearing strength, and upon disturbance the soil will just flow like a liquid. Okay, so Here we can see the corresponding IL value is greater than 1. That is, we see the IL value is greater than 1 means same here. The water content is greater, smaller than that of my plastic limit of the soil, right? So in that case, it's greater than 1 means my water content is greater than that of my plastic limit of the soil, right? Now suppose my IC value is 0. Okay, so IC value is 0 when liquid limit it's equal to my water content of the soil sample. That is, my water content is at the liquid limit. So we can say, see, my consistency index is near about 0. So in that case also we can say my consistency is plastic and it's a very soft kind of soil, right? So now when IC value is greater than 1, let us suppose is 0.25 or 0.5, when my IC value is greater than 1. Here it's greater than 1, right? That means my soil is in a semi-solid state or in a solid state, right? See, it's in a semi-solid state or in a solid state, and we can say it's very stiff or very hard, right? So this is the case of my consistency index. Now we can also just look on my liquidity index. So liquidity index usually varies when it will be between 0 to 1, right? We see when the liquidity index is for 0 to 1, we can say soil is in a plastic state. See, corresponding to the IL value 0 to 1, my soil is in a plastic state, right? So this liquidity index can be also useful as like that of my consistency index also. So we can just observe these two equations or these two IC and IL ratio, define this definition, and we can just simply write IL it's equal to 1 minus IC, right? Starting the corresponding value of IL and IC, we can tell what is the consistency of soil. Okay. So classifying the soils based on activity number, we can look through this table. So we see if the activity number is less than 0.75, it's an inactive type of soil. If activity number is between 0.75 to 1.25, it's a normal soil. If the activity number is greater than 1.25, we call it as an active type of soil. So basically what we can infer from this activity number is the soil type, like we see with this inactive, normal and active. But what is the engineering significance of calling the soil active or inactive or normal, right? So usually we can expect higher volume change in soil. That is, we expect higher compressibility, higher swelling with higher values of activity. That is, suppose my activity number is greater than 1.25. We have already talked about what is my activity number, right? So activity, suppose my denoted by A, it's equal to the plasticity divided by C, and C is my percentage of my clay size particles by weight in a soil sample, right? So suppose we say if my activity number is greater than 1.25, and suppose we have a soil which has my activity number between 0.75 to 1.25. So we call it as a normal, we call it an active soil. So suppose this is soil type A and this is soil type B. So what will be the difference between the two type of soil? So this soil B type will have higher compressibility and higher swelling than B, soil A, right? Because B soil is more active, right? So it's more susceptible to shrink or swell than that of soil A. So we can easily get an idea about the engineering performance of the soil. So suppose we are dealing with two types, so definitely B, which will have higher compressibility, we will try to avoid using soil type B as a foundation material and will prefer more soil type A, right? So in this way, judging on the activity number will be helpful in determining the engineering performance or the properties of the soil. So we can also show this in a graph, suppose. So this is my soil type B, and suppose this is my soil type A, and this is my plasticity index in y-axis, and I have my percentage clay size particles in the x-axis, right? So this is my activity of soil when B has higher activity than that of A. Okay. Now, since we have already started talking about how this activity number has its significance, we should also talk about what we learned about in the previous slide about the plasticity index, the liquidity index, or we talked about consistency index, right? So basically, we know that these Atterberg limits are all found out in thoroughly remolded soils, determined on the remolded type of soil. Yet, we see that these Atterberg limits, although very arbitrary, very empirical, they are very much used for this classification of these fine grained soils for engineering purposes, right? This is because both the Atterberg limits and engineering properties, they correlate well and found to be influenced by the same set of factors, such as the natural structure of a clay soil, or the pore water, or history of the soil deposit, right? So the use of the indices and the consistency limits are very much important. So we see here we talked about activity number, right? So judging on the activity number, we can determine the compressibility of the soil, the swelling characteristics, right? We previously talked about the plasticity index of the soil, right? So the plasticity index is mainly dependent on the amount of the clay mineral present in the soil. So a study of the plasticity index and studying in reference to the liquid limit of the soil can help us to determine the type and the nature of the clay, as the liquid limit and the plastic limit both are dependent on the amount and the type of the clay present in the soil, right? So we have already seen the liquid limit is between 0 to 1, right? So what will happen? In that case, the soil will behave like a plastic state, right? Now, when our liquidity index is greater than 1, we see that the soil almost behave like a liquid and flow like a liquid only when, right? Or we also talked about our consistency index of the soil, right? Like when my consistency index is negative, the natural water content of the soil than the liquid limit, and the soil mass will behave like a liquid upon disturbance. Or if the consistency index is greater than 1, the soil will be very stiff or very hard, and accordingly we can determine whether it can be used as a foundation material or not, or any other construction purpose. So we already talked few about these in the previous slide, like how we can classify, tell about the consistency of the soil based on the numerical value of IC or IL. Okay, so also suppose like the liquidity index is less than 0. In that case, the soil will be very hard, right? Or it will behave like a brittle solid, and when sheared it will have fracture, right? So we can draw a close relationship between the Atterberg limits and the engineering properties of the soil, and we can tell about the characteristics of the soil, which will give us various indication about how the can be suitably used for a civil engineer. Okay, so an engineer will be able to get a picture of the engineering behavior of soil knowing its Atterberg limits, and this will be very clear from the table that is shown in the slide, which gives a very extensive empirical correlation between the Atterberg limits and a number of engineering properties of the soil, as it is written, like the dry strength, the compressibility of the soil, the permeability of the soil, the rate of volume change of the soil, right? So all these are engineering properties which are correlated with Atterberg limits. So like suppose we can see my two columns, that suppose you want to compare soils which has equal liquid limit, and it's my, but the plasticity index is increasing. So my plasticity index, it's basically WL minus WP. So my liquid limit is kept constant, and this my IP is kept increasing. So what happens when plasticity index increases? Dry strength increases. And suppose my plasticity index now remains constant and my liquid limit, it's increasing. So liquid limit increasing means my soil have a decreasing dry strength. So my dry strength will decrease. Now what is my toughness? So toughness, the term we already came across in my previous slide, but I didn't in it. So for now let's leave this, and we will explain this later when we will more be familiar with the term toughness, when we will talk about the determination of liquid limit in the laboratory. We'll talk about toughness there. So we are more familiar with the term compressibility, right? So an important indication of the compressibility of the soil can be obtained from the liquid limit of the soil. So greater is the liquid limit, greater will be the compressibility of the soil, and in that case we can decide that general compressible soil usually avoided as foundation material, right? So we see when my plasticity index is same and my liquid limit is increasing, we can say my compressibility of the soil increases, right? In the case when my liquid limit is same for both the soils, only the plasticity index, we can say that the compressibility remains almost same. Okay, now let's talk about permeability of the soil. So permeability is basically the ease with which water flows force of the soil, right? So we can say that if my plasticity index is increasing at equal liquid limit, my permeability of the soil decreases. And contrary, when liquid limit is increasing with equal plasticity index for both the soil, we say that the soil with greater liquid limit have greater permeability. That is, my permeability increases. Right? Now my rate of volume is more or less related to the compressibility of the soil. So same, we see that if my plasticity index is equal with liquid limit increasing for both the when comparing two soils, we can say with a greater limit my volume change also increases, like my compressibility of the soil. For plasticity index increasing with equal liquid limit, we say my rate of volume change decreases, as opposite to soils with equal plasticity index but my liquid limit is increasing. Right? So these are of determining the Atterberg limits greatly is of practical usage. So we have talked about the significance of these indices and how these indices influence and is correlated with determining the engineering properties of soil. So this table will be very much useful to determine the characteristics of the soil when studying of the plasticity index or the liquidity index. Right. So that's all for this lecture. We will meet ahead in the subsequent lecture about these various laboratory tests for determination of liquid limit, plastic limit or shrinkage limit. We will also talk about some other terms like sensitivity of clays or thixotropy of clays. Other terms which we related to fine grained soils, mostly clays. Right. So we will also solve certain problems which will be helpful in getting a more clearer picture of the Atterberg limits and how this Atterberg limits, the numerical values which we will use in classifying the soil and will give us an idea about the engineering properties of the soil. So, thank you.